Hi guys, welcome back. I just want us to look at electric circuit graphs, right? The basics that you need to know. On the left, we have graphs that are usually given to us when we are investigating Ohm's law, which speaks about how for a constant resistance, the potential difference across the conductor is directly proportional to the current through the conductor, right? So when we do that investigation, we get a graph that looks like this. I have two graphs, the one in blue. I just want to highlight the important things to note from the graph or from analyzing the graph, right? One of the important things to note is that the gradient, what is the gradient equal to in each of the graphs? Let's start with the one on the left. Gradient is change in y over change in x. In this instance, if you look, it's going to be change in V over change in I, right? So it's very important that you must be able to use Ohm's law and fit it into the equation of a straight line, right? So this basically and that means that the gradient is equal to the resistance. So we can use the gradient of this graph to calculate the resistance, right? While if you look in the other graph, what do we have? We have a slightly different situation where we have the inverse of this, right? Which would also mean it's going to be equal to the inverse of resistance, because the gradient here would be I over V, not V over I, but change in I over change in V. So the gradient of this graph is equal to 1 over r, right? And the intercept is obviously 0. The intercept there is going to be obviously 0. So what I mean when I say you must be able to fit it into the equation of a straight line is, for instance, if I am to rearrange this to this format, you will see that these are your y values, these are your x values in the first graph, and this would be your gradient, and your intercept is going to be 0, right? It's going to be 0. That's what I mean when I say you must be able to fit it into the equation of a straight line. Then coming to the one on the right, this is the one that we usually given. So in the one of Ohm's law, we usually given a situation where you are just looking at the current and the potential difference, and often they say ignore the effects of, or rather the internal resistance in the wires and in the resistance in the battery, right? Different from the one on the right, where we do have internal resistance. Let me actually include it to show that, where we do not ignore internal resistance. So it will often be shown like this, and then you have that R there, and then across the battery, then you've connected a voltmeter V, and you are taking readings from there. Usually in this investigation, we are looking at trying to find the internal resistance and the EMF of the battery, right? And what is important is that when this switch is open, there's no current flowing in the circuit, so which means the reading you get on V is the EMF. So when current is 0, the reading that you get, which is equal to your intercept, is going to be the EMF, right? EMF. And then the moment you close the switch, then your voltmeter is going to read the external voltage, right? So what that means is, now let's explain why the graph is decreasing. If I have, let's say V external plus IR, this is the V internal, basically the product of current, total current, and internal resistance, right? If, let's say for instance, this is a constant 20, and let's say the V internal after you close the switch is, let's give it 15, and the V external is 5, right? This is a variable resistor, which means you can change the resistance here. Let's say they increase, or rather they decrease the resistance, and that means they're going to increase the current, because current is inversely proportional to resistance for a constant EMF, right? So let's say that situation is happening. This is still fixed because I'm still using the same battery. If I change the current, I haven't changed the battery, so the internal resistance is still the same, right? But if I increase the current by decreasing the resistance, that means that the product, this is going to increase, the product as well is going to increase, right? If this is fixed, just to make an example, a hypothetical example, to say this went from 5, let's say it's now 2, this is still fixed. What does that mean? That means this must have increased now to what? To 18, to still make up the total of 20, right? So you will notice that, pardon, let me just go back there. I said increase, so not 2, let's make it increase to 7. I hear myself contradicting myself there. So it's going to increase, let's say, to 7. And then this would have to decrease to 13 to make up the total of 20, right? What I mean, or what that means in terms of the graph, is that you will see that as the current increases, we said the current increases, the V external is going to decrease. That's why the graph is decreasing. So after the switch is closed, then the V we are reading is the V external, right? Why is all of this important? It's important for me to be able to understand this graph, because now let's go back to say this equation that I'm using to describe what is happening in this graph. How do I fit it into the equation of a straight line, right? This is my Y values, this is my X, and this is my intercept C, right? So if I rearrange this equation, V external is equal to negative Ri plus C, which is EMF, right? Then what does that mean? That means in this graph, basically, Y is equal to mx plus C. The negative R, or the slope, is equal to negative internal resistance, right? So obviously the slope is negative because the graph is decreasing. But when I'm told to write down the value of the internal resistance, it's going to be a positive value, right? And then this is how this graph would fit into the equation of a straight line, and how you should understand it in terms of getting gradient and getting internal resistance, right? I hope that was very helpful to you, and please subscribe and recommend the video also to anyone who may find it helpful, and I'll see you on the next video.